Okay, well, it looks like we're up to 26 people, so I'm gonna go ahead and get started. Let's do this. Well, thank you everybody for joining today's DCSEU webinar on energy modeling for BEPS. My name is Ajit Naik. I'm a PE and energy and commissioning engineer with Baumann Consulting. I'm joined today by my colleagues Scott Emery and Oliver Baumann. Today we'll be giving a presentation on energy modeling for BEPS. So our intention today is to cover a few different learning objectives. So we want to first understand what the DC building energy performance requirements are and how they apply to buildings in the DC area. We want to understand what the predictive building energy modeling process is and how it differs from other types of energy modeling. We want to understand the role of predictive energy modeling in developing strategies for both new construction and existing building projects to meet BEPS requirements. And we want to learn about a real world case study that used energy modeling to chart a BEPS compliance strategy. So as we go through this presentation today, please use the text box to type in any questions that you might have. We'll stop periodically to address the questions. We'll also have some time at the end of the webinar where we'll unmute everybody and allow everybody the chance to ask questions. But if you think of anything as you go along, please go ahead and type them into the box, and I will periodically stop, and my colleague Oliver will ask them to me. We'll also be using live polling at a few junctures throughout this webinar. So when you see polls come up, please pay attention and remember to submit a response to your poll. So to kick things off today, I'm going to hand off the mic to my colleague Scott to talk a little bit about BEPS.
Okay, thanks, Ajit. So if you're working in DC, you should be at this point aware of the Building Energy Performance Standard. This is a new standard which went into effect January 1 of this year. It's based on the 2018 Omnibus Energy Bill or Energy Act that the City Council put in place. And just to try to give just a quick introduction to what Building Energy Performance Standard is, you see here kind of a standard distribution curve. And the reason this curve here is kind of to give you an idea of how this policy works. This policy essentially says that your building needs to perform to meet a minimum level of performance to be considered compliant with the standard. And that compliance is based on essentially grading buildings on a curve. It looks at the different types of properties in the city, and it sets a standard that's at least the median score, median energy performance for each property type. So offices are compared to offices, schools are compared to schools, multifamily residential compared to multifamily residential. And what happens over time, if you can give me a click, advance the slide, Ajit, is the score. What happens is you have to improve. If you're below the median, you're going to have to work to improve your energy performance to comply with the policy. And so what that's going to happen is that's going to shift our curve to the right. So as of today, as of 2021, this applies to buildings 50,000 square feet and higher in the private sector, 10,000 square feet and higher for the city-owned buildings. And every 6 years, the standard is reset. So the expectation is we're going to improve energy performance over time, and that curve is going to shift to the right. And so that median is also going to shift to the right. And that's going to mean that over time, and we've done some analysis at Baumann, we expect that over time, very few buildings will avoid having to do something to comply in the future, meaning there's going to be a need for a vast majority of the buildings in the city to improve their energy performance. So the important thing to know here is that it's a standard that's set based on the median performance of buildings. It's reset every 6 years, and the policy is going to drive energy performance up across the city. Move to the next slide, Ajit. So we're in what's called BEPS Cycle 1 now, and essentially what's happening is work that's going on. The properties that have been notified, and you should have already been notified or received notification if your property doesn't comply with BEPS, they have now roughly 5 years to comply with this policy. There's more details there, but generally speaking, by 2026, you need to do something to be in compliance with the policy. By 2027, your building will be reassessed, and you'll be determined if you complied with the first cycle of BEPS or not. And then there'll be a new cycle of BEPS that starts January 1, 2027. At that point, it will be expanded to include buildings down to 25,000 square feet And then that process starts over again in 2033 when buildings down to 10,000 square feet will be added to the process. So again, the point to be aware of is that BEPS is going to cause the energy performance to continually be reset and driven down. And we're in these cycles today, and you have a certain amount of time to comply. There are a couple of ways that you can comply right now, or the basic way to comply now is if you already have a building that performs above the median, you're in compliance and you should be okay until the next cycle comes along. However, you may want to look at how close you are to the compliance standard. And I don't believe, if you want to go to the next slide, Ajit. Yeah, so here's an example of some of the standards that are in place. Now, these may have been tweaked a little bit. This slide is from a few months ago, but they're generally accurate. So if you look at this, if you have a hotel building, if you have a Energy Star score that's 54 or higher, you comply with BEPS. If you're below 54, you're not in compliance if your hotel is larger than 50,000 square feet. You see that some of these properties don't have Energy Star scores. So if you can't get an Energy Star score, you're then compared to the source EUI, the median source EUI across that property type. So when we look at, say, convenience stores or gas stations, they have a median source EUI of 592.6 kBTU per square foot per year. And so you need to be below that number. You need to have your score below it. So these are the numbers that you're looking at, and these are based on your benchmarking data from 2019. So if you already are either above the Energy Star score or below the median energy source EUI, then you're in compliance and you're good until the next cycle. However, if say you're an office building and you have an Energy Star today of 72, keeping in mind that that curve is going to be shifting to the right, then you're going to be in a position that you're going to need to possibly work on improving your energy performance, or you're going to be faced with having to do something to comply in the next cycle. Next slide. So the other way you can comply if you don't improve your energy performance is you can be faced what are called alternative compliance penalties. And so these penalties are in the thousands of dollars. They start at $10 per square foot. And the base starting point is it's going to be 500,000 for a 50,000 square foot building. So 10 times 50,000 gets you 500,000. Now there are some adjustments. We won't have time to go in that today. There are some ways that number can be brought down from the get-go. And I'm going to talk just in a minute about how you bring them down over the next 4 to 5 years. But as you can see, this is a significant penalty, and it goes up to $7.5 million. Now, the point of the penalty is not for the city to collect money. The point of the penalty is to encourage building owners to do something to improve their building energy performance. In fact, the money that would be collected under this penalty system or alternative compliance path of paying a fine would be going into a pool that would help buildings improve energy performance. So if you don't spend the money in your own building, the city will collect a penalty, and then that penalty will be paid into performance enhancements of other buildings. Now, again, the goal here isn't for people to pay penalties. The goal is for people to improve their energy performance. And so let's talk about the other options you have to comply without having to pay a potential high penalty if your building's in non-compliance. So there are 4 basic pathways. There's the performance pathway, which simply means what that says is it looks at if you're below one of those goals, if you're below the median performance level, then between now and 2026, you need to reduce your building's energy performance, your site energy performance by 20%. So that 20% is just right off. It's going to be based on your 2018 and 2019. Now, this is based on a COVID adjusted schedule, but your average 2018 and 2019 energy use compared to your energy use in 2026, if that 2020-26 use is down 20%, you would comply under the performance option. This gives you the most flexibility as a building owner. You figure out, how do I get 20% energy use out of my building? The next option is called the standard target. So if you're an office building and you are, say, at a 65 or a 66, you're not far away from that 71 Energy Star score. So what you would need to do is by 2026, you would need to get to that 71, and you would be considered compliant with the current BEPS cycle. And there's a schedule of values that DOE has provided that we have that information, and we can look at your building and tell you how low your Energy Star score can be in order to make doing the standard target make sense. So essentially, if 20% energy improvement would get you to the standard target, then DOE is suggesting you want to consider the standard target. The other thing to know about the standard target path, if you go on that option, Like in that example of that office building that say has a 65 relative to a 71 target, there is a reduction right off the top of their score because they're close to the target to begin with. I don't have time to go into the details there. Feel free to send an email or reach out to me and I can explain that a little bit more or help you calculate that. But that's a real benefit of the standard target. If you already have a pretty high performing building that isn't quite all the way to the standard, you can still reduce your score from the beginning. Now, option 3 is a prescriptive path. I mean, let me make one more comment about option 2. The standard target is a path that gives you also a lot of flexibility. You basically just have to decide you're going to go on that path. So the first 2 paths, you have to hit the target literally to not have to pay a penalty. Now that penalty is adjusted at the end, you get partial credit. So if you're shooting to reduce 20% and you only reduce 15%, your fine would be reduced 75% in that case because you've made it 75% of the way to your goal. The third option is what's called the prescriptive path. And the prescriptive path is going to give you certainty. What you have to do with the prescriptive path is you have to go through an energy auditing process. You have to select measures. You have to implement those measures. And then if you implement those measures, regardless of how you perform, you will be considered compliant and you won't have to pay a financial penalty. An important point to note here is option 3 has a number of reporting requirements with the city. You have to implement a very specific O&M plan. You're going to have certain meetings and certain milestones that have to be met over the course of the next 3 to 5 years. It has a lot more reporting requirements, but it gives you the certainty that as long as you follow through what you agreed to do with the city, you're going to be in compliance. And then the last option is the alternative compliance pathway. And so the alternative compliance pathway gives you some other things where you can either say overachieve in the first cycle and you get credit in the second cycle, or you can agree to overachieve in the second or third cycle and get some leeway in terms of compliance during the first cycle. Now, the one thing I want to comment on here is, and I'm running out of time, but I will make the segue to our discussion on modeling is throughout this process, you really have to have some certainty that you're going to do something that's going to achieve a certain level of energy performance achievement. Even in the prescriptive pathway, what you have to submit to the city is going to have to show that you have identified savings of up to 20% or more in your property that are going to hit those targets as agreed to under the standard target or performance target. And so energy modeling plays a key role here because what we have to do is look at your existing property. We need to look at how your current building operates and performs. And I'm just going to explain how we do that in this type of modeling process. And then we can start looking at your choices and options of things that you might do. If you might be, say, you have an old chiller and we look at replacing that chiller, or if you have an envelope that's not performing well, we can start looking at different envelope options and different scenarios of tightening the envelope, replacing windows, et cetera. And we can start calculating how much energy that potentially saves in your building and how much chance you have to meet the different criteria of complying with BEPS, which helps you decide how you want to comply. One last comment I want to make is if you have a property that is not in compliance, you need to make a choice of which option you want to go with by February of 2023. So that seems like a lot of time, but if you push it out to February 2023, you then have, April of 2023, they've changed that date, April 2023, you then have until basically the end of 2025. So you've really got very little time to implement things. So I encourage you to think now if you have properties that don't comply, and I encourage you to, as we learn from Audit going forward here, use tools like modeling to make sure that you're making smart choices. So Audit, with that, I'll hand it over to you. And if I have another slide, feel free to just click past it. Thanks.
Thank you, Scott. I appreciate you giving some context to what we're going to talk about today. So that's really the big picture about what BEPS is and why you should care, and how energy modeling can basically help achieve BEPS goals. So we're going to dive into the technical egg-headed portion of this in just a minute. But before we get into that, Oliver, I was wondering if you could launch the first poll question. I wanted to ask what the backgrounds are of everybody in the audience today. So you should have just gotten a poll question that popped up on your screen that gives you the options of architect, engineer, sustainability professional, building owner, student, or other. So there's 42 of us on this call today, and I think the 3 of us presenters can't vote. So let's wait until we get a few more out of these 38 folks. So you got another 10 seconds. All right. That seems good enough. Oliver, you want to run it? All right. So it looks like today we've got 1 architect, 9 engineers, 16 sustainability professionals, 2 building owners, and 6 others. Those of you who are others, I would love it if you told us what your backgrounds are in the Q&A chat, just so we can have a little context of who's all here today. So, well, thank you guys for that. So it looks like we have a pretty diverse mix of people, but all folks who kind of work in and around buildings and who are familiar with buildings. So that's a great audience for today's talk. Okay, so I wanted to talk a little bit today first about what is building energy modeling. So turns out there's a website called energymodels.com that has a pretty great definition that I like. It says energy modeling is the virtual or computerized simulation of a building or a complex that focuses on its energy consumption, utility bills, life cycle costs, and various energy related items such as air conditioning, lights, and hot water. It is used to evaluate the payback of green energy solutions like solar panels and photovoltaics, wind turbines, and high efficiency appliances, just like Scott indicated is important for BEPS. To understand energy modeling, it's important to understand building simulation. So what is building simulation? So I asked Wikipedia for this one, and Wikipedia told me that building performance simulation is a replication of aspects of a building using a computer-based mathematical model created on the basis of fundamental physical principles and sound engineering practice. Basically, this is technical jargon to say, instead of building a building in real life and testing it to see what happens, you build one on a computer and test it to see what happens and make decisions about what happens in real life based on your model. There are lots of different types of building simulation. Today we're here talking about energy modeling, but there are lots of different types, and I want to briefly touch on them just so you're aware. Daylight analysis is a form of building performance simulation that calculates daylight quantity. You can do it things like visualize glare, like we see on screen here. We can do it to assess whether spaces have enough light in them from natural lighting, and whether they have too much light, too bright lights from natural lighting. There's embodied carbon analysis, which is a simulation of a building that allows us to estimate the amount of carbon emissions that were needed to get all the building materials to site. And there's a CFD analysis, which is the simulation of air and thermal flows in a space to predict temperature, humidity, and comfort levels. So energy modeling is just one piece in a large world of building performance simulation, but it's all fundamentally the same idea, using a virtual model of a building to predict how it'll actually behave in real life. So what that looks like for energy modeling is physically building an actual 3D model of your building, and then providing inputs, things like weather data, properties about the enclosure, like thermal insulation of walls and roofs, and the thermal and optical properties of windows. We look at things like occupants, the number of people, what they're doing inside of the space, how often they're in the space, when they're in the space. We look at appliances, again, the type, their number, their power draw, the amount of heat that they give off to the space, and their usage profiles. We need to know about building lighting, that's artificial electric lighting, how much is there, how is it controlled, how many watts are connected, and when is it generally used. We also look at inputs for HVAC, again, the type of HVAC system, the fuel source, whether it's gas or electric or maybe district energy based. We look at set points and control strategies for HVAC systems like supply air temperatures, supply airflow rates, water flow rates, and water flow temperatures. We also look at water heating. That's water heating for your showers and your sink use and your sinks. And again, the same thing. We look for temperatures, the amount, fixtures sizes, rated fixture flow rates. And lastly, utility rates. That's not just the dollar per kilowatt hour of your electricity. We can also use tariffs, time of use pricing, demand-based pricing, etc. So really, it's a pretty comprehensive model. All of the information that you need really to build a building and operate a building in real life, you also need this information to build an energy model of it. And once you've gone through the trouble of building this virtual energy model of your building, you're rewarded with outputs. For example, you get predicted energy use. This is useful in a number of ways. You get it broken down by end use, as you can see in the graph on the right. So the energy model will not just tell you how much energy your building uses per year, but it'll tell you where that energy goes. Whether, for example, on the right here, we have several end uses like heating, cooling, fans, pumps, miscellaneous gas appliances, miscellaneous electric appliances, lighting, etc. Different projects can have different end uses, but these are kind of the big players that you'll see here. We're also able to get peak loads out of energy modeling software. So not just how much energy, say, does the heating system use in a year, but what's the peak demand that it uses at any one time. This type of information is very useful for sizing equipment and selecting HVAC equipment. Lastly, but not least, we get utility cost out of this, cost savings. It's not just about energy savings, but any energy modeling study always has to take a look at the costs as well. Lots of times when we talk about energy use in buildings, especially under the framework of energy modeling, we talk about energy usage intensity, or EUI. So generally, this is the amount of energy a building uses per year divided by its floor area. So if you see this terminology referenced throughout the rest of our presentation, that's what it refers to. So on the whole, that's what energy modeling is, and that's kind of how it works. So I'm going to pause here. Do we have any questions so far? That's just a comment from the DCSU, which says, "Good morning, gentlemen. Good session so far. Just a friendly note. We've heard from DOEE already, and they'd like to use the term compliance payments instead of penalties. So let's use that going forward and consider this presentation revised in session."
We just got, yeah, I think that's not a really question. That's more a comment in the
okay.
So
got it. So back to energy modeling, we have a concept of what energy modeling is, how it works, and we need to know when it's used. So we've been talking about using building energy modeling for BEPS, but that's not really where building energy modeling is mostly used today. Building energy modeling is mostly required for two main reasons. Number one is it's required by local energy code to get a building permit in DC. Not for every project, but for a lot of new projects, especially projects like new construction with large amounts of glass, or existing buildings with historic facades where the facade isn't being touched or insulated as part of the renovation process. So projects like these are often required by DCRA to develop an energy model in order to demonstrate compliance with energy code and get a permit. There are also other places where the energy modeling is required as well, primarily for third-party building certifications like LEED. So LEED awards points for energy modeling buildings, and I'm sure with a lot of you as sustainability professionals on the call today, you're well aware of this fact. So most energy modeling today is actually done for compliance, whether with code or with third-party certification requirements. So this type of energy modeling is called compliance energy modeling, and it's not really suitable for BEPS strategies, and we'll get into why as we go through a little bit. But just a brief overview on what exactly compliance energy modeling is. So basically, as discussed, it's an energy modeling process that evaluates whether a building is in compliance with energy code. It actually requires two energy models. One of your actual building, whether new construction, major renovation, or what have existing building. You have to develop a model of that. And then you have to develop another model for an imaginary baseline building, which has the same shape, the same program, the same occupancy, operating parameters, all of that. But the enclosure, the MEP systems, everything else is at code minimum. So it's an imaginary building, one that you're not actually building, but considered the code minimum version of what you're proposing. So then, in order to evaluate energy code performance, your proposed design is simply evaluated against this imaginary baseline building. So if your proposed building shows a better performance than the baseline by some predetermined minimum specified percentage, then the building is considered in compliance with code or will achieve points for LEED or another third-party sustainability certification. This performance is typically assessed in terms of energy cost, annual energy cost, or a related derivative of that number. And really, the critical thing here is it doesn't actually matter whether the real world performance of your project after it's all done and occupied matches what your compliance model showed. It's not relevant. The only thing that's relevant to the compliance model is what percentage better your design shows over this imaginary baseline building. So it's there's a few things about this. So there are two real rules that define how the compliance modeling process works. One of them is ASHRAE 90.1, and the other one is the International Energy Conservation Code. All energy codes around the country usually draw from one of these two, with some exceptions. DC, however, is no exception, and the energy modeling rules for compliance in DC are based on ASHRAE 90.1 2016. LEED version 4 bases it on ASHRAE 90.1 2010. There's a few things about all of these compliance modeling rules, though, however. They allow modelers to use standard default assumptions for several values instead of, actually identifying real world values. This is especially, common in new buildings where you might not know some of these parameters. Things like air tightness, usage profiles, internal loads, or even weather data. We can just use average values or standard default reference values for these, as long as they're used exactly the same in the proposed as well as the baseline building. So what this means is the compliance model outputs frequently diverge widely from real world performance down the road. So again, while compliance modeling is essential for demonstrating compliance with energy code, it might not be so useful for actually figuring out how much energy your building is going to use and figuring out where to invest to improve your building's performance. So what this brings us to is predictive energy modeling. So predictive energy modeling is, it also involves building an energy model, but using it differently. It is a process that uses an energy model to reliably predict real-world building energy use. It relies on simulation inputs that accurately reflect all real-world aspects of the buildings and don't use standard reference values. It also involves addressing uncertainty in assumed variables in the simulation and addressing it with analytical techniques to improve your confidence. This model can then be used to assess the impact of potential energy conservation measures under consideration. And that's true whether this is an existing building seeking to improve its performance or a new construction or major renovation project seeking to make sure that it will be it will meet BEPS requirements after the project is complete. Finally, it's also critical that a predictive energy model can later be successfully validated by monitoring after the implementation of the Ecms. So to kind of summarize, there's a few critical ways that compliance energy modeling, which many of you may be already familiar with or have done, is different than predictive energy modeling. And it can really be summed up at 3 points. Number one, the method. Whereas compliance modeling is just about your performance relative to an imaginary building, predictive modeling is about actually figuring out how much it's going to use. Compliance modeling doesn't have a lot of input fidelity. You're allowed to use default and average values, whereas predictive modeling requires you to do the due diligence and figure out the real world or likely values. The outcomes also vary. Compliance modeling is considered successful where the proposed model is just better than the baseline model, regardless of how it performs in the real world, while predictive modeling is only considered successful if the building's performance is measured afterwards and can validate what was predicted by the energy model. So those are the salient differences between predictive energy model and predictive energy modeling is really what's relevant for BEPS. So I want to talk a little bit today about how predictive modeling can help existing building owners plan for BEPS. So BEPS, as Scott pointed out, is eventually going to come to impact all buildings, but even buildings that are under design and construction today, when they're operational, are going to be, they're going to be under fall under BEPS. So there's a few real steps and ways that the predictive modeling process can help building owners. First, it can help them understand their BEPS target. Next, it can help them contract a building energy modeler to build an energy model based on info collected via document review, stakeholder review, and site visits. Existing buildings have historic data available, usually always in the form of utility bills, and sometimes in the form of trend data from building management systems, smart meters, or other sources. So what this allows existing buildings to do is calibrate the energy model inputs until the outputs match the historical data. So what we're looking at on the right here is an example of that. So this measure data is for a building, if this is just its monthly energy use, is shown by this diamond. Initially, an energy model, after being built to the best of its capability, showed this this square line. There's quite a difference between the measured data and the model data. But after observing these differences and calibrating and tweaking the model inputs, the modeler here was able to achieve a very good match between the model data and the measured data. And once you see that good match, it improves the level of confidence that you have that the ECM analysis, that savings estimation that you're gonna estimate using this model, will also be more reliable and can serve as a better foundation for making significant investments. Once these models have been tested, it's important for modeling practitioners to identify implementation costs for these measures, identify cost-effective ECMs, and then chart a path for BEPS compliance.
Archit, we have a quick question here.
Sure.
Why is compliance energy modeling done against an imaginary building and not a similar building type already existing?
That's a great question. So really, the purpose of energy code is to determine how the minimum that anybody can do, right? So that's how energy code works. It always defines the minimum. You cannot do less than this. And the energy code allows users, when they're doing a little bit worse in one area. For example, energy code typically requires buildings have not more than 40% glass. You'll see lots of very glassy buildings walking around DC today. So how did they get around this? They had to build an energy model that showed that their design performance was gonna do better than code minimum. So rather than the way energy codes are structured today, is rather than compare to actual peer buildings, it's always about fundamentally, how are you doing more than the bare minimum? It's a regulatory approach to it, which is the ultimate reasoning behind it. Oliver, Scott, any other further comments on that?
Nope.
Okay, all right. Well, hopefully that answered the question. And it's relevant to our next part. So existing building owners have a clear motivation to use predictive modeling. How about building developers? So building developers, of planned building projects, they never have historic data available to aid with calibration. And sometimes they even lack clear definitions of what the planned building operation might be. And all of this increases the uncertainty in the predictive modeling process. For example, a spec office building might not have a good idea of who their future tenant is going to be in the early phases of design. However, understanding who those tenants are and how they're going to operate it is going to be essential when thinking about BEPS, right? For example, a tenant that runs 24/7, like a call center, is probably going to use more energy than a typical office tenant that only works 9 to 5 Mondays through Saturday. And the ECMs that impact one might be totally different from another. For example, the tenant that runs 24 hours a day will use a lot more lights at night. So high efficiency lighting might be more important for them. So for new buildings and new projects where there's a lot of uncertainty, the process looks similar but has a few tweaks to it. First and foremost, it's critical to understand what the BEPS target will be, no different than an existing building. It's important to build an energy model that's based on detailed and reliable building information. In this case, for a new building, it would be collected via design document review, stakeholder interviews, and also integration into design meetings. So it's very critical that energy modelers and service providers be integrated into the design team so they have a better understanding of the proposed building that's being designed. When there's no historic data available, what we do is we perform a sensitivity analysis on uncertain model inputs instead of calibration. So for example, what that literally means is once we build that energy model, that might be a ways off of the actual data, just like we had for existing building, there's that gap there. We don't know what that gap might be, so we test the energy model sensitivity to different parameters. For example, if we don't know how often what kind of occupant density might be in a space, for example, a call center might have people packed in much tighter together than a law office. So we can run the model with both options to see how it performs. So there are many different things, and that's what you're seeing on the right here. This is an energy model with all sorts of the sensitivity study shown for all sorts of different parameters. So for example, air tightness, what happens if the building is assumed to be tight versus leaky? We notice that there isn't a huge difference. However, we look at things like the HVAC system, which have a much larger, both positive and potential negative impact on the system. So it's things that we can look at include things in sensitivity analysis, include different daily operating hours, seasonal operation, partial occupancy levels, different thermostat set points, hotter or colder than average weather, user error, like forgetting to switch off the lights in the windows. Building these types of sensitivity analyses into the energy model allows the modeler to understand the potential impact of ECMs. And generally, the ECMs that that consistently provide savings or performance improvement across a wide range of different scenarios should be selected, as well as those ECMs that provide improvement under the most likely scenarios should be selected. So while it's not quite as good as calibration and doesn't improve the confidence to the same degree, a sensitivity analysis is absolutely essential in any project where historic building data is unavailable, like a new construction. So this really leads us to the predictive energy modeling process. Whether you're working for an existing building or a new building, the process is basically the same. You work to establish goals, such as energy and economic goals, and those should be made with all building stakeholders. We then collect building data, including project documentation, stakeholder interviews, design team meetings for new buildings, site visits, utility bill, and measured trend data for existing buildings. It's really important to validate this data, especially trend data. And ways of doing this are usually good engineering judgment and where necessary for existing buildings, measurement to validate that data as well. Then we develop an energy model. We use this to analyze the building energy usage breakdown, as well as, and it's really critical to implement a quality control process to verify inputs and outputs. Those inputs and outputs should be, the QA/QC process is typically done by peer review. So once you build an energy model, it's really essential to have another qualified energy model sort of review that data. Next, it's addressing model uncertainty. So in the case of existing buildings, this involves calibrating your energy model until it matches those utility bills. And for new building projects, performing a sensitivity analysis for unknown variables to quantify uncertainty. Lastly, it's very important to facilitate decision-making. It's important that both the building owner and the modeler have a clear understanding of the goals. Owners will rely on these results to inform significant building decisions. So it's very, very important that this be a transparent process. It's very critical that the modelers work with other project stakeholders to obtain ECM costs to understand the financial side of this so that those economic goals can be addressed as well as those energy goals. And lastly, it's critical to advise the project team on what cost-effective comprehensive strategies are to meet the goals. It's not enough to just say what the possibilities are, but the modeler should help to facilitate those key decisions. Lastly, modelers should help with validation. Predictive energy modeling process should clearly document the energy model inputs and outputs for future transparency, then should also work with the project team to incorporate monitoring requirements into the design. As previously discussed, one of the essential components of predictive modeling is that it can be validated later on. So modelers should work with the project team to understand how that performance will be validated and make sure that those performance monitoring requirements are actually included in the design.
Ajit, we have two questions.
Sure.
One directly related to this slide here. Who is responsible for collecting building data?
Great question. So I would say that's it's ultimately the modeler's responsibility to get the due diligence of what information they need, but that information will typically come from the building owner and the project design teams throughout the process. Collecting information can be a painstaking process and a very difficult process. It can involve many different things, especially for existing buildings. It can involve asking and requesting old project documentation like as-builts, equipment submittals, maintenance logs, O&M plans, install manuals, records of previous upgrades and renovations, access to the building management system. It can involve site visits, stakeholder interviews. So it's really on the building energy modeler to understand what they need to ask for, but this information will come from other project stakeholders.
Okay, thank you. And there's another question actually in the chat here. I think this will be covered just in a moment in the seminar here. Has DC BGS developed EUIs and Energy Star rating for its schools and offices? If so, what are they? I'm not 100% sure if that question refers to the general benchmark that needs to be met by all buildings, or if that's specifically for DGS buildings, so district-owned buildings.
Scott, how about I pitch this one over to you?
Yeah, sure. Well, first off, they fall under the BEPS requirements. So city-owned buildings are part of that program, so they have to comply with BEPS. Beyond that, I do believe they have sort of separate overall programs and objectives to meet the city's long-term requirements, which are a 50% greenhouse gas reduction by 2032. And then I believe it's a greenhouse gas neutrality by 2045 or 2050. And so I know that, those requirements apply to the schools, DGS buildings as well. So they're part of the whole program that's BEPS. I can't tell you specifically if they have some other, sort of standard that they're currently designing and building to, but I do know they have to comply with that program and are working towards those bigger city goals of reducing greenhouse gas emissions and ultimately greenhouse gas emission neutral by the mid-century.
Thanks, Scott. Thanks everybody for asking great questions. Please keep them coming. We love it. So, now that we've walked through the predictive modeling process, I want to talk briefly about when energy modeling should be incorporated into really any project. So this is called an impact curve for the energy modeling process. Really, there's a few different curves here. Number one shows the ability to impact cost and the functional performance of the building. It drops as you go along in projects. Number two is the cost of design changes. We have a few architects on this team, on this call today. You guys definitely know that as a project progresses, the cost of design changes increases. So typically, a traditional process that doesn't involve predictive energy modeling with respect to BEPS doesn't kick modeling until kind of later in the design process. And that can it really isn't happening until your ability to impact costs and functional abilities has dropped and the cost of your design changes has already started to creep up. So really, it's critical to engage early energy modeling early in the process. So whether it's a retrofit analysis for an existing building and you're thinking of a capital investment plan, or you're working on a new building project and the owner is kind of thinking about BEPS, it's going to pay off to incorporate this process early. I'm going to take a little segue here and talk about another project, not in DC, but relevant. This is a project a couple hours down the road in Virginia Beach that we worked on a few years ago, the Brock Environmental Center. That is a net zero building. Net zero buildings are similar to BEPS in that they have a fixed performance target. If you do not hit that performance target in real life and measure it, it's not deemed successful. So in that way, it's just like BEPS. So this building needed to comply and hit basically zero on-site energy, and it did. During the design, we were looking at a few different options. Architects on this call will know that changing the thickness of your wall or changing the dimensions of your window isn't something that you can do easily later on in the design process. Changes your building area, your building dimensions. It's something you have to do right at the beginning. For this, we actually took a look at what was the cost effectiveness of different ECMs? For example, we looked at really, really thick insulation, which might seem crazy in Virginia Beach, but for a $22,000 investment, we were able to save about 27,000 kBTUs per year. That's about 8,000 kilowatt hours of electricity, about $1,000 a year. So not a great payback, 22 years, but the alternative was to provide PV. So to generate as much electricity on site as we would have offset by installing that installation, we actually needed to bring in $44,000 of PV. So it actually costs twice as much to install that PV as the installation. While PV, it's easy to add at the back end, adding in thick insulation is very difficult to do unless you kind of have that in mind at the beginning of a project. So in order for this to successfully happen, that modeling had to happen early on. Similar story, PV versus triple pane windows. Triple pane windows, again, might not sound necessary for Virginia Beach and maybe not as dramatic, but again, it was less expensive to invest in triple pane windows than it was to invest in PV in order to hit that target of net zero performance. So just like net zero, when you come to BEPS, you have a target and there is a ramification for not hitting that target. So it's always critical to keep that in mind when you're weighing ECMs against each other. There's a lot of software and building performance tools available on this. I've included several logos of popular energy modeling software on here. This is not all. There are literally hundreds of tools that do this. These are just some of the more popular ones. There's a directory provided by the International Building Performance Simulation Association. Yes, that's a thing. They maintain a directory of software used all around the world for this purpose. A couple that I want to point out at least are Open Studio, which is a free energy modeling software published by the National Renewable Energy Lab on a DOE fund. So anybody looking for a place to start, that's a reliable and free energy modeling tool. However, I'm not saying that's always the right tool for the job. Which modeling tool you use is highly dependent on the nature of the project and what it involves. What tool might be right for one project might not be right for another. The same way that a surgical scalpel might be good for some things, but probably not for chopping down trees. There are several key resources for building energy modelers and stakeholders that you might find useful. Number one is ASHRAE Handbook of Fundamentals. It contains lots of things that are useful for energy modeling, predictive energy modeling specifically, like climate data, reference tables, and info regarding the building, like for materials, HVAC systems, appliances, things of that nature. It also provides the basic rules of how energy modeling should be performed, like the science behind it. There's ASHRAE Standard 209, which talks about the modeling process and specifically how it applies to new building projects. There's ASHRAE Standard 211, which is the standard for commercial building energy audits for existing buildings, which also goes into quite a bit of detail on how to energy model and calibrate energy models for existing buildings. There's other standards like ASHRAE 189 that provide just recommendations for what are good design strategies for high performance buildings. And there are also other guides. For example, the AIA put out a guide for integrating energy modeling to the design process, which is really great for a guide for helping modelers also talk to architects. The Rocky Mountain Institute also put out a guide called Building Energy Modeling for Owners and Managers. So these are really great resources for stakeholders, practitioners, owners, and design teams alike to improve communication between all parties. Lastly, there are forums available like Unmet Hours and EnergyModels.com, as I previously mentioned, that are a place for practitioners to meet, connect, and ask each other's questions to improve their craft. We're going to talk about a case study, specifically an office building case study. But before we go, I wanted to ask a question and ask people, what is the median Energy Star score of an office building in DC? So typically the poll is just opened up. So please go ahead and provide your response. The way that this works is that 50 is an average building. So all buildings nationwide would have a score of 50. So that's the average of all office buildings in the entire country. But the buildings in DC might be a little bit better, a little bit worse. So where do you guys think they stack up? We have 18 of 40 people responding so far. So I'm going to give folks another 10 seconds to guess what they think the average building, office building in DC performs at. They're coming in thick. 5 more seconds. All right, Oliver, you want to run it? Okay, so across the board here, right, we have everywhere from 41, which would be a little bit worse than the average of 50 nationwide, all the way to 71, which is pretty solid. The right answer for this building, as Scott mentioned, is actually 71. So that means that buildings in DC, office buildings in DC, perform better than 71% of buildings nationwide. So that means the office building stock in DC is already pretty efficient. And as you guys recall, the BEPS requirements are based on average building performance. So office buildings in DC have to do better than an Energy Star score of 71 in order to be considered as meeting BEPS requirements. Okay. So I want to talk about the case study here. So the building that we're talking about is a real life building office building in Northwest DC. Not going to tell you what the address is, but please rest assured that this is in fact a real building that we worked on very recently. It's about 62,000 square foot, 5-story office building. And the owner, heard about BEPS and kind of came to us asking what that might look like. So we took a look at it. It's a 37% window to wall ratio. It's an all electric building built in 1968, but has been upgraded in recent years, including window upgrades, lighting upgrades, fan coil replacement, baseboard heater replacement, and conversion of air handling units from constant to variable volume. So still, this building was showing a site EUI of 53.3, which gave it an Energy Star score of 66. So based on the current rules, we estimated that this building could be subject to penalties as high as $62,000 or $620,000, excuse me. That's that $10 per square foot figure.
Compliant payments.
Compliance payments. Yes, $620,000 in compliance payments, or else they needed to meet one of those strategies that Scott talked about earlier. So looking at that performance, as Scott mentioned, for buildings that are at that 65, 66 Energy Star score range, they're really pretty close to 71. In fact, when we ran the numbers, we determined that this building would only really need to reduce its energy usage by 7% to meet the BEPS requirements. So not a huge improvement. So that option 2, that standard target, is what was relevant here. Just pursuing this would allow them to reduce that maximum penalty to somewhere in the neighborhood of estimated $210,000, and it could even further reduce or even eliminate it if they actually meet that goal.
Hey, Ajit.
Go ahead.
Yeah, I think that 210,000 number, is that for that reduction, or is that based on their already proximity to the score? Do you remember?
It was their proximity to the score.
Yeah, so based on their proximity to the score, they would already be reduced to that $200,000 range.
Yeah, so still quite, thank you for that clarification. Still quite significant, and probably money that could better be spent by the owner on their own building. So the process again here is the same as we discussed. First was to understand the BEPS target and confirm it with building ownership. So we recommended to begin with 10% reduction by 2026 and not just 7%. To account for variability in building operation, uncertainty, etc. And after discussions, we actually bumped this up to 13% to better position the building for the next BEPS compliance cycle. We collected a ton of building information. We did a thorough document review. We looked at as-built drawings and submittals. There were several renovations. We looked at all of those drawings and submittals. There was a previous facility condition assessment and an energy audit done, which we looked through, and we looked through all of their 2019 utility bills. We interviewed stakeholders, including building management and ownership, the facility staff, as well as current tenants actually occupying the building. We visited the site to verify the building operations. We physically put eyes on all of the systems, enclosure and HVAC and MEP. We took an inventory of all of the equipment inside of the building. All of this was really critical to not use those standard default reference values that we would normally use in compliance modeling. All of this is what's required to make it an effective predictive energy model. We then calibrated the energy model inputs until the outputs matched the utility bills within 10% as required by ASHRAE standard 211. Actually, 5% is recommended, but so long as you're within 10%, it's considered acceptable. We then used this calibrated model to test potential ECMs. We reached out to relevant contractors and used cost estimating software to estimate what these costs would be. We identified measures that only had an acceptable payback period, and then we charted a cost-effective path to BEPS compliance. So before, I'm going to go into a case study actually in the software for about 20 minutes just to familiarize you guys with what the process looks like. But I have one last question in a building, one last poll question today. Where does most of the energy in a typical office building go? So there's a poll question that just popped up for all you guys. So before we're going to put together an energy model here for this building, we're actually going to walk through the process in the energy modeling software to see what that looks like and answer this question for ourselves, at least for this specific building. So let's see here. I'll give you guys 5 more seconds to go to respond before we close the poll. All right, looks like about 70% of you have responded, so we're all good. So the vast majority of you selected cooling, with a second coming in as heating and a third place as lighting. So pretty good guesses. Let's see how it actually happens as we put this energy model together. I'll progress here. We're going to actually show a case study in RETScreen software. So you should have all received a link to download RETScreen when you registered for this program. If you haven't got it installed, don't worry. This webinar is being recorded and you can follow along at a later date. So RETScreen Expert is an energy modeling software developed by Natural Resources Canada. It's available for free online, though you can't save files with the free version. You need the paid version for that. Natural Resources Canada is like the Canadian equivalent of the US DOE. So this is a very reliable publisher and a very reliable software. Specifically designed to assess existing building retrofit feasibility. It works on a monthly basis. So for projects like this, where we only had monthly energy bills, it's appropriate to use that. It allows direct comparison of utility bills to assist calibration. It models the interaction between potential ECMs, and it even provides a cost database. Though it's really important to be careful when you see cost databases online. If you're not yourself a contractor, it's an okay starting point, but we really recommend confirming all cost estimates with a qualified relevant contractor so that you don't promise something that really isn't feasible off the bat. RETScreen also has a ton of training. While I am going to go through the software and physically demonstrate it in a minute here, I'm not going to go through every facet of the software. We're really only going to scratch the surface. There is a ton of training available online at this link that I've provided below. It's a YouTube link, so I've just provided shortened here for easy reference. So that's the software we're going to use today and some of the reasons why we chose it for this existing building process. Again, we're going to take a look at what that looks like. But before we start today, I also have provided an anonymized version of the model file that we actually use for this project. So the completed energy model file is available for download at this Dropbox link at the bottom. So that's bit.ly/3BQMDQD. So you can download this file and play around with it, use it for reference, and also follow along here today as we go through this model. I'll leave that on the screen for another second so anybody can copy it down who needs before I jump over into the software. Okay, So here I've got a blank copy of RETScreen software. So let's assume that, we've done our site visits, we've collected all of the data that we had about this building. We understand its enclosure properties, how it's operated, its HVAC systems, its lighting systems, its hot water systems, its pool, anything else that it might have should be included here. Our first step is to identify the location of the building. This being a Canadian software, its default location is Montreal. So what we'd look up is where this building is, Washington, DC. Pop up a map for us, and it will allow us to select areas. So for example, here I've selected Reagan Airport. It's not quite in Northwest DC, but close enough. We'll call it a victory. So we select that, and it'll immediately update our project to be located in Washington, DC. So predictive energy models need to use real weather data. So RETScreen actually pulls NASA's climate data for the time zone that, or for the time period that you selected. It will actually provide you with real world weather data. So this is a great start for the predictive modeling process. Next, we have to define parameters about our building. So our building here is a office building. Sorry, guys. So our building is an office building. So we select commercial institutional property, and it already defaults to office building. So we could provide information about it. For example, this is a Northwest DC office building located in Northwest DC. So we know that this facility was specifically about 62,000 square feet, so specifically 61,855. So we enter that. This is the US, so we use BTUs to represent EUIs. And we determined via Energy Star Portfolio Manager, as discussed earlier, that a Energy Star target of 71, an Energy Star score of 71 correlates to a site EUI of 49.7. The building, based on real world actual measured data from utility bills, had an Energy Star score of 66, which correlated to a EUI of 53.3. We discussed that -7% was enough to just barely meet the BEPS requirement, but we actually ended up targeting a 13% reduction over the current value to make sure that we account for any uncertainty, and also sort of position this building for the next upcoming BEPS cycle. So we can kind of see where our base case is and where our target is, and what kind of fuel savings we need to get there. Next, we want to define our building parameters. What all is inside of our building. This is the part where we need to accurately and realistically reflect what our building looks like. We'd start out with electricity and fuels. This building is an all-electric building, as I mentioned, so natural gas isn't really relevant, but the DC market charges about this building 13 cents per kilowatt hours. I'd want to put in building schedules, such as, its space heating set point, call it 70 degrees. That's what they keep it at. The space cooling set point, as well as when the building changes over, typically been between heating and cooling, call it 65 degrees. We want to look at now defining different parameters of the building. So for example, we'd want to define the building envelope. So, we have the option here to define all different aspects of the building, including, walls. We could actually go in here and point out this building has 1302 square foot of walls in the north, 74 square foot on the east, 6860 on the south, so on, so forth, until we've accurately built basically 3D model of how this building works. We go in and enter different R values of the insulation, and carry on this way until all aspects of the building is fully defined. So this includes walls, windows, doors, and roofs. This includes heating systems like, boilers that are present, furnaces, water heaters. For example, this building has a cooling system on site. So we could look at the type of cooling system that it is, specify, that it's an air-cooled chiller, specify its capacity, even specify its manufacturer, model, all of this information that we collected while we were on site. In RETScreen, you'll notice that there's always two options: a base case, which represents your existing building as it is today before implementing any upgrades, and a proposed case where you enter the building as you're proposing it's going to be, those ECMs. We typically recommend starting out by putting in the exact same information for both the proposed and baseline case so that the results are exactly the same. Then we will calibrate the energy model to the input data to make sure that it's within that 5 to 10% range before we go in and test our actual ECMs. So we would go through this and continue setting up the building, envelope systems, heating systems, cooling systems, power systems, lighting systems, all of that jazz until we fully define the building. So
actually, we have a quick question.
Shoot.
What type of weather file does RETScreen use? TMY3?
No, so RETScreen does not use averaged weather data. So for those who are unaware, TMY3 is a set of weather data that's published every hour for different sites around the world. And those values are a 20-year average. So for example, in that file, the temperature on February 3rd at 9 o'clock in the morning is going to be a 20-year average of like the last 20 years before that TMY3 was published. And it'll give you that value. So while that's appropriate for compliance modeling, that's not appropriate for predictive modeling. So what you do is you define the time period that your model is being compared to real data for. And this actually pulls the NASA climate weather station there, and it'll pull that data for the time period you selected, and it'll use it during the modeling process. Do we have another question there?
No, that was all. Thank you.
Okay, all right. So back to this. So I've going to show another, excuse me. So I'm going to switch back from the file that we created that we were just looking at now and look at this, excuse me, I'm going to close out of the blank file that we created and looked at and open up the, open up the RETScreen file that I posted the link to earlier. So this is actually the completed energy model file in RETScreen for the building, that office building in Northwest DC. So all of the facility parameters have been set up the exact same as we did before, that it's an office building, it's located in DC, that it's benchmarked at 71 Energy Star score, has a EUI of 53.3, and is looking for a 13% improvement. Over at the Energy tab, we have fully defined all of the equipment here. So as you go in and take a look, you'll see that electric coils, water heaters, the air-cooled chiller, the building envelope. So all of this information has been provided. Air handling units. There's an existing solar water heater that already serves the pool that's on site. So this building has now been fully designed. So what we'll do is, as I mentioned at the beginning, we don't turn on any of the efficiency measures. We compare our base case to our proposed case, and we perform the exact same. When we look at how this energy model compares to our historical energy data, we found a variance of 15.3%, right? So that means after we built our energy model and then calibrated it against those real world utility data, we had a variance of 15.3%. So that means this model, as uploaded, isn't ready for doing that ECM analysis. There's something inappropriate with the inputs that make it not accurate enough for this type of assessment. So we went back on site, took a deep dive into what went on, and we actually realized that there was a partial glazing upgrade. And we had assumed that the windows were all single pane everywhere and they were really old and bad, but were actually quite a bit better performing than we assumed. We found a cut sheet for what these values were, and increased and actually modeled the U value of those windows appropriately. So before, where we assumed they were very high and poorly performing windows, we hadn't accounted for that window upgrade, which improved that window performance. So after updating the model, going back to the comparison screen, it actually brought the model to within 0.02% of the actual annual energy use. So this model is now considered calibrated by looking through all of the inputs and verifying that they're faithful to the actual building and addressing any places where there are discrepancies. We were able to make our model consistent to within less than 1% of our actual model, of our actual measured data. So what we did now is, now that the model was calibrated, is to enter energy efficiency measures. So we wanted to understand where the energy in the building was going. So we asked earlier what the primary end uses of energy in an office building in DC are, and your answers were: first were space cooling, number 2 was space heating, and number 3 were lights. So for this building, the breakdown was actually a little bit different. Heating was the first use, with space cooling coming in a close second, with electrical equipment, which include things like plug loads, things like appliances, computers, escalators, all of that. And lastly, the number 4 came in lights. So that's what the breakdown looked like for this building. So that's also where we targeted our ECMs. We looked into, for example, in cooling, replacing the existing chiller, air-cooled chiller, with a water-cooled chiller that has significantly higher efficiency. We looked at building envelope improvements of further improving the windows from double pane glass to triple pane glass, and several other measures, including improvements to lighting, improvements to the existing solar hot water heater, and adding photovoltaic panels. So that brings us to our energy model results. So we wanted to see what would happen if we included all of these measures that we proposed there, all of the measures that we designed. And you can see that they range in values and paybacks from all the way to some of these efficiency measures payback immediately, and some of them take like 300 plus years to pay back. So we had discussed at the project outset with the building owner that any measures with the payback over 20 years were going to be unacceptable. So we click the target button and choose a maximum limit of simple payback of 20 years. So when we run this, it should eliminate all measures with savings periods over 20 years. And you can see that everything with 300 plus years has all been eliminated. So we have a lot fewer measures to consider. So now that we've sort of eliminated any of those measures that are just no-go on the basis of their long payback period, we can understand how this building might actually perform. So now that we've eliminated all of those sort of high payback measures, we'll again look at our building comparison. So looking at our baseline case and our proposed case, we have a total energy savings of almost 30%. So if we implement all of these short acceptable payback period measures, the building could achieve a savings goal of 29%. Of course, that costs quite a bit of money though, and the plan only calls for an improvement of 13%. So it's now really up to us as the modeler to work with the building owner, prioritize these ECMs, and individually make a go, no go decision on each one. So looking back at these measures again, the owner was willing to invest in anything that costs less than $20,000, really a low cost measure without too much additional consideration, but really was hesitant before spending anything over $20,000, which they considered a capital investment measure. Taking a look through this, we were able to eliminate some things off the bat. So we talked to them about eliminating the air-cooled chiller, but since the chiller uses R22, which is a banned refrigerant, the building owner prioritized its replacement. So we looked to eliminate all other measures that were capital improvement and out of budget, such as upgrading the pumps, implementing retro commissioning, and installing photovoltaic panels. So we have a lot fewer measures here, but except for the capital measure of investing in the chiller, the rest of them are all low cost, no cost measures that pay back quickly. So looking at the comparison, we actually now have a much more reasonable energy savings achievement of 16%, which is much more in line with the plan goal of 13%, aligns with the owner's existing goals for equipment upgrades, and also is financially feasible. So bringing it back here, we really tested a ton of ECMs here, right? There were low cost and no cost recommendations and capital efficiency measures, and all of them contributed different parts or different amounts to BEPS, to meeting the BEPS requirements, but all of them had different values and different acceptabilities. So, you know, the outcomes here were that we set a goal of 13%, identified potential ECMs, built a calibrated predictive models to test these ECMs, help the owner categorize them based on simple payback as go, no go, and maybe, helped owner evaluate the go and maybe measures in terms of their priorities, like eliminating banned refrigerants, along with energy requirements and financial requirements. And we ultimately selected a comprehensive strategy that met the energy, financial, and other project goals. So in a nutshell, that's how to deploy predictive energy modeling on existing building projects that are facing a BEPS compliance cycle. So just a few conclusions today to wrap things up here is to note that BEPS is a new regulation in DC that requires buildings to comply with these real world performance targets based on benchmark utility bills. Only some buildings for now, but by 2033, it's going to be basically everybody. Buildings that don't comply with BEPS face ramifications, potentially including compliance payments. And so predictive building energy modeling is the process that accurately predicts building energy modeling or building energy performance and can be used to inform investment decisions. And this process is different from that compliance modeling sometimes required by code and third-party certifications. This energy model really needs to have highly accurate inputs, and the uncertainty needs to be addressed either via calibration process for existing buildings or via a sensitivity analysis for new building projects, including major renovations. And all buildings must have a quality control process to, again, improve the reliability of the model. And lastly, predictive energy models can be used to assess the performance impact of potential energy conservation measures to develop cost-effective strategies for BEPS compliance. So that's all we had for today. So I'm going to open it up to any questions that we might have. Seems like a couple of them might have been typed in, so maybe we can start with those, Oliver.
Okay, yeah, we have a few more questions, so I go in the order as they came in here. Can you use this model for just lighting retrofits to LED lighting?
No, this can be used for any type of retrofits that you can think of. RETScreen is an extremely detailed energy modeling software that has lots of capabilities, as do others. We talked about lighting, realigning the tubes on their solar collector that heated their pool, implementing chilled water outside air temperature resets, chiller replacements, PV installations, retro commissioning mechanical systems, upgrading windows. So really anything that you can think of mostly can be modeled and considered here for feasibility.
Okay, then another question, and I'm not really sure who can actually answer that. Who should I reach out to at DCSEU or DOEE to discuss my interest in providing assistance to building owners and or BEPS modelers with data collection processes?
Wow, you know, as a modeler, I'm not really sure I'm qualified to answer that, though I do know we have some folks here from DCSEU if anybody wants to chime in on their opinion about this great question. I'm looking at you, Mark. Oh yeah, I might need to, okay.
Yeah, Mark,
go ahead.
Go ahead, Ashish.
Mark responds, please email us at info.dcseu.com. That is info.dcseu.com.
It's info@dcsu.com.
Did I not say at? Sorry, it's been a long webinar.
I'll add it to the answer.
Okay, thank you, Scott. So I'm
Okay.
sorry for that non-answer there, but please reach out to the DCSU. All right, go ahead, Oliver.
Okay, next question. Good example. What is a typical cost range to the property owner for project development services in the example Ajit just walked through?
Oliver, I'm actually going to defer that question to you.
Well, I defer that to Scott because he writes the proposals.
All right, sorry, I was typing an answer. So what's our
How much does
question?
it cost, Scott? How much does it cost?
To do
Like that
what?
project that we walked through, what's the cost point for the services?
It really ranges from, I would say on the lower end to do a complete assessment, which is included an energy audit. On the lower end, the buildings we're looking at are in the $15,000 range, really, to do things properly and go through all the documentation, review, simulation, adjustments, and assessment of EEMs, plus doing analysis of costs. And then it can go up there for more complicated buildings. Typically right now they're in the more, I would say the upper side of an first level, an assessment is in the 20 to 30,000 on the higher end for a complex building. But
Okay.
it's hard to do it for, it's going to be in that 10 to 15 at the lower end to get a real quality result.
Okay, thank you, Scott. And the next question is, could you discuss electrification as a BEPS compliance strategy to reduce site EUI? Can energy models assist in making a decision to electrify certain systems?
I'll say with the caveat, yes, with the caveat, right? So the Energy Star score is based on source energy. So I really wish I had this slide here. I don't in this presentation, but the Energy Star score works on source energy. So source energy is not how much energy you use at the building, right? Like what your utility bill is. It also includes all of like the generation and transmission losses it took to get that energy to you. So the source, so electricity, being that it requires a power plant and power lines and all of this stuff, typically has a lot higher source factor. It's about 3 times higher than gas. So if you're converting from a gas heating system to an electric heating system, it certainly can be an energy efficiency measure, and it certainly could be something that you identify with an energy model, but it won't impact the Energy Star score 1-to-1. Since there's that factor of 3 there, your new electric system is going to have to be at least 3 times more efficient than the gas system to achieve similar improvements in your Energy Star score. Scott, I know there are also some pathways for reducing your site EUI. So I'm not sure
Right.
this would help in that framework. Can you comment on that?
Yeah, sure. So I did want to make that point so if you're non-compliant currently, then the requirement is a 20% reduction of site EUI. And certainly converting a, say, fossil fuel-based heating system to a heat pump system will reduce your site energy. It's a very efficient technology, but you do have to pay attention to that balance between your site energy and your source energy. So the ironic or possible tricky part is you could get that 20% site energy reduction, but if you don't have a really super high efficiency heat pump solution, you may actually increase your source energy, which would increase your Energy Star score. But one thing I would add here is I do believe that the law, I know that the law requires either next year or 2023, there has to be a review of whether or not this program would be switched to a carbon emission reduction rule as opposed to an energy reduction rule. And early indicators are it's likely that eventually it'll become a carbon emission reduction. So that could also, show a benefit of going away from fossil fuel on site, because fossil fuel on site would lock it in. But we can definitely do those assessments, but it's a little bit tricky to look at those details as Ajit alluded to.
Great
Okay.
question.
We have one more comment, another contact at BCSEU for the previous question that's posted in the chat. Right now, I don't see any other questions.
Okay, well then, thank you everybody for making the time to come and join us today and talk about energy modeling for BEPS. Hope you guys learned something here and can take this back to your projects and the buildings that you work on, and can deploy this process ultimately to make the district a more efficient place. So thank you all, and we'll let you have your 4 minutes back till 11 o'clock.